Okay, now we want to get this result for the expectation of a sum. Uh, Very useful result. Um, should make sense, nothing too strange. So if I I'll start with this proposition for a different way to compute the expected value of x. So suppose x is a discrete random variable and there's this underlying sample space then with countable number of outcomes. And we suppose that the range of x is can be it's countable also, so we can just call it like little x1, little x2, dot dot. So e of x then is from the definition of e of x is this. And now the trick is I write this term here as a sum of probabilities of the outcomes. So this is equal to sum over I, say 1 to infinity if you want, xi. And then this just becomes the sum of p of s, where, say, x of s is equal to little xi. So there's this these underlying outcomes that map to that value xi. So I grab all of them and I take the sum over all s. So I forgot to write that, little s in big S, where p of s, where x of s is equal to xi. Okay. Well, now this is summed over s, and this is constant with respect to that, so I can certainly bring that in there. So I have a sum over I, sum over little a. I get a chance to write this again. I get a redemption. Little s in s, x of little s equal xi. Here I have xi, little xi, p of s. Well, if x of s is equal to xi inside that sum, then I could also express this as x of s. So this is just the sum I, sum s in s, x s equals xi, and I can write xs ps. And now I just realized this is every s in s, counted exactly once. Traversing over all the values in the range, and I just count all the inputs in the domain that map to each one in the range. So that's just all the s in s. So this is just equal to the sum, single sum now, s in s, xs ps. Okay, I know it seems a little abstract and a little silly, a little easy maybe, but it's useful just to really get this, believe this. So maybe we could do a little example. So for example, suppose we let x equal sum 2 dice. All right, then I could compute e of x by the definition. So this is the definition way. Take each value. So it's 2, 1 over 36 plus 3, 2 over 36 plus 4, dot, 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 plus 12, 1 over 36. All right, I just go through. So 11 terms. And remember, this is 7. Let me do it. Or using proposition, e of x is equal to, so using proposition, I just take the value of the random variable and I sum over all the 36 terms. So it's going to be, to do it in its gory detail, it would be 1 over 36, the probability of every outcome, then x of, say, 1, 1, plus 1 over 36, x of 1, 2, plus 1 over 36, x of 2, 1, plus dot, 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 plus 1 over 36, x of, if we were to imagine going all the way in order, sort of 6, 6. So this has 36 terms, but of course it's the same thing. Here, these are aggregating 2 of the 1 over 36 terms. So you can see this corresponds to these 2 here. So this corresponds to these 2 terms here, right? This is 3 and 3. Okay, and each one has a pair there. So that's really just what we just proved up here. So this is also obviously the same thing. It's equal to 7. Okay, so now we want to find the expected value of the sum of 2 random variables that are on the same sample space. So now let both x and y be DRVs, both on S. All right, well, E of x plus y, what should that mean? That should mean the sum, or that should be the sum over all values of x plus y. But you see, that's a little tricky to figure out, right? We don't know what the values x plus y can be without going through and actually figuring out what all the sum values are, right? So, for example, if say x is equal to the roll on die 1 and y is equal to the sum of 2 die, what are all the values of x and y? And furthermore, what are their probabilities? So that would just, I mean, we could do it in that case, but it's hard to have a general way to say that. But if you think about it, if that is what they are, then I can actually do it by outcome pretty easily. So, so let's see. Do I talk about that first? Yeah. So let's say first. So let's write a question mark here and see if we can get a little bit with this example. So suppose x is equal to value on first die, and y equals sum of 2 die. So these are both random variables on the same sample space, right? Here's x maybe. Okay, here's x maybe, and here would just be 1, 1, 1, 1, 1. Right? This is one of those things you're supposed to do ahead of time. So here's x. And these are the, this is supposed to represent the sample space. Each cell is an outcome. So each cell is an S. And probability of S is equal to 1 over 36 for all cells. And, you know, over here, if I had y, I would have the usual sums. So here's y, and I would have like 2, 3, you know, here's 10, 11, 11, 12, etc., right? And same here, each cell is an S with the same probability. So, what is the expected value of the sum? Well, what is the so this is the thing. If I go after what the possible values of the sum are, it's impossible. But if I just stick with the idea that for each cell I get a sum, right? So for each cell I get a sum, so I can make a picture here of the combined one. So here's a picture of x plus y. and I get this combination here. I'm getting a little stressed because I thought I could do this in one. I'm not sure. So 1, 2, 3, so a little bit uneven. That's okay. So I'm in here, and now each cell is equally likely. And if I say hit this cell, well, then x plus y is the sum of these. It's easy to do, right? This is 3. And this would just be all of these I would add 1 to. So 3, 4, 5, 6, 7, 8 along here. All of these I add 2 to, so this would be 5. What the hell would be next? 6, yeah, 7, 8, 9, 10, yep. These I add 3 to, so this would be, normally it would be 2, 3, 4, so this would be 7. Yep, and so 7, 8, 9, 10, 11, 12, etc. But the probability of any one of these happening is the same as the probability of this, the probability of this. In every case, if I go on a cell-by-cell basis, the probability of each one of these, so P of S equals 1 over 36 here too. Okay, and this is my result. So E x plus y, then, I can use the previous proposition and just realize that I just need to add x and y at that outcome. So this is just the sum. It's the same sample space, so little s in big S. And I just add xs plus ys, and of course, multiply by the probability they occur from this argument above. Okay, but notice, so this would be like doing it by hand. But notice, this is also equal to, you just distribute, and this is equal to S in S, XS, PS, and I can just distribute. So this just gives me E x plus E y from above. Okay, this is extremely useful. Let's see how much time. Okay, we gotta stop, and I will carry this over on the other side.